Oh, great Odin's raven!
So we're going to do a quick overview of proofs and algebra examples related to angles, segments, triangles, and parallel lines. Before we do that, I'm going to review some of the key theorems and definitions related to these kinds of questions. So first, a definition of midpoint. So if I have a diagram related to this, a conclusion that I can make from that using definition of midpoint is that the midpoint cuts it into two congruent segments. So let's write that down. Okay, so M is a midpoint if and only if, which is a biconditional, so this can work in both directions when using it in proofs. AM is congruent to MB. You could also write that as the lengths are equal, so AM equals the length MB, and recall that with the segment over it, that's actually talking about the segments. Without the segment, it's just talking about the length of the measurement. So this is biconditional, so if I know that M is a midpoint, then I can conclude that the segments are congruent to each other, and vice versa. If I know the segments are congruent, I can conclude it's a midpoint using this definition of midpoint. It's different from the midpoint theorem, which would conclude that AM is half the measure of the entire segment. So the theorem is different from the definition and will be used in a different way. Segment bisector. If I have something which is bisecting the segment, I'm going to give it a name, say L. Say this is line L, and it bisects this segment. Well, L bisects segment AB if and only if, which is again one of those biconditionals. So I'm using two different notations. This is the double implication, means the same thing as if and only if, the two different ways of writing it. It passes through a point P, which happens to be the midpoint of that segment. P is the midpoint of segment AB. Okay, so the definition of segment bisector lets you move between something being a midpoint and a bisector, whereas the midpoint definition of midpoint lets it be between a midpoint and segments being congruent. So note that if you wanted to show that AP is congruent to PB, what you would first need to do is use this definition of segment bisector to conclude it's a midpoint, and then use definition of midpoint to conclude that the segments are congruent to each other. Okay. Just like we have a definition of midpoint and a segment bisector, we have angle bisectors. So the angle bisector given this diagram, we can define that, would be as follows. Let's say BD, the ray BD, bisects angle ABC, if and only if, which is again a double implication. The two angles that it's splitting it into are congruent to each other. So that would be angle 1 is congruent to angle 2. So this ray BD is cutting this entire angle into two congruent halves. Okay, so that's the definition of an angle bisector. Now we're going to run through several theorems kind of quickly, so if you need time to write them down, feel free to pause them. But ways of proving angles are supplementary and complementary. There's three of each. To prove something, two angles are complementary to each other, so how that would look would be, how that would look would be something like this. Angle 1 complements angle 2. One is from the definition of complementary, which is basically given that their sum adds up to 90. I would be able to conclude this. Also vice versa, since it's a definition, it's biconditional. If the exterior sides of two adjacent angles are perpendicular, then they're complementary. That would be a situation like this. Here are the exterior sides. I'm then going to draw another line in between them so that I can create two adjacent angles. So angle 1 and angle 2 are adjacent to each other. If their exterior sides are perpendicular, meaning they form a right angle, then these two angles would be complementary. It's pretty self-explanatory from the diagram, it's just we need a way of describing that, which is what this does. And then finally, the acute angles of a right triangle are complementary to each other. So if I have a right triangle, these two acute angles are complements of each other, angle 1 and angle 2. For proving something is supplementary, I'm going to get rid of this. proving two things are supplementary to each other, a lot like complementary. The definition, which is that they add up to 180, so much like this, only instead of 90 it would be 180. If two lines are parallel, then their same side interior angles are supplementary. What that would look like would be something like this. If I have two sets of parallel lines being cut by a transversal line, then their same side interior angles, which are the angles which are on the same side of the transversal and on the interior of the two parallel lines, those two angles would be supplementary to each other, and also the same side interior angles of a parallelogram are supplementary to each other. Now there's a number of statements that you can make straight from a diagram. So here's a list of some theorems that you could use in a proof of conclusions you can make straight from a diagram. So let's use a diagram as an example to see how each of these are used. The segment addition postulate basically says that the sum of any two components of a segment is equal to the length of the entire thing. So for a segment addition postulate, that would be used to justify conclusions such as AB plus BC is equal to AC. The sum of the two component segments is equal to the entire segment. The angle addition postulate, this one, would be very, very similar to the segment addition postulate, except in this case I'd be talking about angle 1 and angle 2. So I could say that the measure of angle 1 plus the measure of angle 2 is equal to the measure of their combined angle, which is ABC in this case. And if it turns out that ABC is a straight line, I can actually jump right to the fact that they are 180 degrees. So it's the two parts of the definitions of the angle bisector theorem. Vertical angles being congruent, that's a situation where I have basically two lines that intersect, then their vertical angles, which is the angles on either end, would be congruent to each other. That's a conclusion I can make straight from the diagram using vertical angle theorem. And the exterior angle theorem, which is when I have pretty much any polygon. So let's go with, I'll do a hexagon as a general example. It's a huge hexagon. Let me make that a little bit smaller. If I have a hexagon and I draw an exterior angle, the exterior angle theorem is if I have a triangle, here I'll draw a triangle, and I draw an exterior angle of one of its sides here. This exterior angle, whatever it be, here would be equal to the sum of these two remote interior angles. Okay, moving on, difference between substitution property and transitive property. Recall we had all these properties of equality, the addition property of equality, subtraction, multiplication, division, the symmetric property, and then there was always, it's a little bit tricky to tell the difference between substitution property and transitive property. So a general rule of thumb you can use to separate those two properties is that substitution property pretty much deals with equalities when you're substituting a value in an equation, and the transitive property pretty much deals with congruence. So if you're dealing with a congruent situation, you're not sure if it's substitution or transitive, go with transitive. If you're dealing with an equality situation, you're not sure whether it's substitution or transitive, go with substitution. Okay. 5 ways of proving congruent triangles. Well, we have the side-side-side postulate, the side-angle-side postulate, angle-side-angle postulate, angle-angle-side theorem, and the hypotenuse leg theorem. Now recall or notice that for each of these, you will need 3 pieces of information. 3 pieces of info before you're able to use each of these theorems. Now, you might be asking yourself, Mr. Burke, that's crazy. Hypotenuse leg theorem clearly only has 2 pieces of information. Well, remember that whenever you use the hypotenuse leg, and that should say theorem, make sure you correct that you must first have a right triangle. So it being a right triangle is the hidden piece of information you would need in order to use this hypotenuse leg theorem. It also only applies to right triangles, whereas the rest of these apply to all triangles. Okay. One other note is that notice that these are named by their corresponding parts. If you're unsure or have questions about how you would identify which of these theorems or postulates to use, we can go over that tomorrow, so please make a note of it. Once you've proven triangles are congruent, however, you can use the corresponding parts of congruent triangles are congruent to each other. And note that these parts, the parts of the triangle that I'm talking about, could be angles or sides. So it's a way of proving angles or sides are congruent to each other. Okay, moving down again, keeping this rapid fire pace up. Looking at the definition of an isosceles triangle, a triangle is isosceles if and only if, so again another biconditional statement, it has two congruent legs, so I have two legs which are congruent. That's versus the isosceles triangle theorem, which actually has nothing to do with the triangle being isosceles, but it says that if the base angles are congruent, or the base angles are congruent if and only if their opposite sides are congruent. So that's the isosceles triangle theorem. So it's two key differences between those two, the definition of the theorem. Finally, definition of perpendicular lines is that perpendicular lines meet to form right angles. So if you were using this in a proof, let's name these lines. I'll call it line L and line N. Line L is perpendicular to line N if and only if, so another biconditional statement, any of these angles, call this angle 1, is a right angle. Now it's just not just that angle, but actually all four of these angles will be right angles if these lines are perpendicular. Okay, so now some properties of parallel lines. Well, if lines are parallel, we can make all of these different conclusions. So what do they look like? Again, given a set of parallel lines, 1, 2, lines parallel, a transversal which cuts across them, I can look at different parts. If these lines are parallel, corresponding angles are congruent. So corresponding angles would be angles which would match up if you drag one vertex to the other. So to identify corresponding angles, here is one angle. And if I take that angle and drag it to the next vertex, I can see that this angle would be its corresponding angle, so they would match up when laid over top of each other. If I wanted alternate interior angles, let's do those in a different color. Alternate interior angles. The angle alternate interior to this one is on the alternate side of the transversal line and on the interior of the two parallel lines. Same side interior, similar setup. Two same side interior angles would be this one and this one. They are on the same side of the transversal and on the interior of the parallel lines. To prove lines parallel, there are actually 10 ways, so here are the first 5. These are the basic ones. If it's pretty much the converse of the 3 that we looked at above. If corresponding angles are congruent, then lines are parallel. If the alternate interior and the same side interior, two other ways of proving parallel. 2 lines perpendicular to the same line are parallel to each other. That would look something like this. If I have 2 parallel lines and a line perpendicular to them, if these 2 lines are both perpendicular to the same one, then they're parallel to each other. And, oops, clear that. 2 lines parallel to the same line are parallel to each other. The other 5 that you're probably less familiar with are ones that we proved after we did parallel line proofs, which look something like this. This definition of parallelogram, it has 2 sets of opposite parallel sides. You can use that to show lines are parallel. Definition of trapezoid, exactly 1 set of parallel sides. A segment which joins the midpoints of 2 sides of a triangle is parallel to its third side. The median of a trapezoid is parallel to both bases. And the triangle proportionality theorem, which we actually went over yesterday, is another way to prove lines parallel. If you're curious as to what each of these situations would look like, be sure to bring it up tomorrow when we meet in class. Now I'd like to actually go over some examples of proofs, and I'm going to go through this one with you, and then I'm going to have you try the next one on your own. But let's see what we can do here. So let's get a pen. I would highly recommend highlighters to help you to mark up your diagram, but I'm going to mark my givens. I know F and H are both right angles. So this is a right angle, and this is a right angle. Well, since they're right angles, I know all right angles are congruent, so I know I have a set of congruent angles. And I know EI, this line, bisects HF. So the segment which is getting bisected is HF. So this segment is getting cut into 2 I know that EI passes through the midpoint of this, which means it's cutting this into two congruent parts. My goals show that E is congruent to I, so I'm trying to get these two angles. Well, if I show these two triangles are congruent, I can use corresponding parts, and since angle 1 is congruent to angle 2 by the vertical angle theorem, I can use angle side angle to prove this. So now that I have a plan, I'm going to write up this proof. I'm going to go down to my statements and reasons, write my givens, angle F and angle H are right angles. That was given to me. Oh, I have a second given. So let's add that in here. I also know that EI bisects HF. It's given to me as well. So I'm first going to say that angle F must be congruent to angle H. That is the right angle theorem. You could also have stated instead that all right angles are congruent. That's basically the statement of the right angle theorem. You don't have to write both. You could pick whichever one you're more comfortable with. But both are equivalent. Next, we're going to say that G is the midpoint of HF. We cannot jump right to the fact that those segments are congruent because I first need to use the definition of segment bisector, which is what we're doing here. And once I know that that's the midpoint, I can say that GH is congruent to GF by definition of midpoint. And finally, the last piece we needed to show the triangles were congruent is that angle 1 is congruent to angle 2, and I'm making that conclusion right from the diagram with the vertical angle theorem. Okay, so now I'm going to scroll down a little bit to get some more space. 6. I now have a angle side angle situation, so I know that triangle EFG is congruent to triangle. Now be careful when labeling your congruents because corresponding parts need to be labeled with corresponding parts. So the vertex that corresponds to E is I, the vertex that corresponds to F is H, and the vertex that corresponds to G is itself G. Okay, that was the angle side angle postulate. I had an angle side and an angle shown already, and I'm using those to conclude those triangles are congruent. So once I know those triangles are congruent, I can say that their corresponding parts, or these corresponding angles, which is E, is congruent to I, because corresponding parts of congruent triangles are congruent to each other. Okay. So with that in mind, I'd like you to try this proof on your own, followed by this one. We will go over both of these in class tomorrow.
This is hard. I am in a pickle.
And this one, try this one as well, number 4. And what I'd like to do now is to go over some algebra type examples so that we can see how these theorems would apply to an algebra type question. So given that the lines are parallel, I know that angle 1 is 3x over 2. I know that angle 2 is x plus 20. I need to find the value of x. Well, notice that angle 2 has a corresponding angle, which would be here, and that these two together form a straight line, so their sum must be 80. So I know that 3x over 2 plus x plus 20. So the sum of these two angles would have to be 180, and that's using corresponding angles of parallel lines are congruent and the angle addition postulate. To solve this, I'm going to multiply the entire equation by 2 to get rid of my fraction here. When I distribute this 2 to every term, I end up with 2 divided by 2, which cancels out, leaves me with 3x. 2 times x would be 2x. 2 times 20 would be 40. And 2 times 180 would be 360. Then I will combine my x's to get 5x, subtract my 40 to the other side, I get 320, and divide both sides by 5, and I get 64. For the second question, it says that it asks a question that tells you PR bisects QPT, the measure of angle 1 plus the measure of angle 6 is 200, OR and VS are parallel. OR and VS parallel. So you're trying to decide, is it the case that OR parallel to VS? So that's my question. Well, I'm going to label this information with you. PR, which is this segment, bisects QPT, which means that by the definition of angle bisector, these two segments are congruent to each other. And I know that angle 1 plus angle 6 equals 200. So angle 1 plus angle 6 here equals 200. I'm going to tell you that no, these lines are not parallel, but I would like you to come up with the justification as to why, and we will go over that in class tomorrow. Scrolling on down to the next example. Okay, we have the measure, angle A and angle B are supplementary to each other. I have the measure of angle A and the measure of angle B, and I need to find A. Well, if they're supplementary, definition of supplementary tells me that the measure of angle A plus the measure of angle B would equal 180, using definition of supplementary. So that means that 4y plus 15 plus 7y would have to be 180, substituting. So substitution property of equality, substituting those values with what they're equivalent to, which means 11y would equal 165. Divide both sides by 11. I get y equals 165 over 11, which is 15. So now my question was not what is y, but what is the measure of angle A. So if I plug this 15 back in to the measure for angle A here, I get the measure of angle A will be equal to 4 times 15, which is 60, plus 15, which would be 75 degrees. And that's my final answer. Moving down, B is the midpoint of AC. AB equals 2x plus 6. AC equals 2 times x plus 7. Well, notice that this AB is 2x plus 6, but AC is the entire thing, which is 2 times x plus 7. So I know that 2x plus 6 would equal 1/2 this total length, which is 2 times x plus 7, using the midpoint theorem. Okay. So now the 2 and the 1/2 will cancel each other out. I'm left with 2x plus 6 equals x plus 7. Subtract x from both sides, subtract 6 from both sides, and I get that x is equal to 1. Okay. Perpendicular, and I had the measure of the two angles. Well, if these two things are perpendicular to each other, that means that angle 1 and angle 2 are complements, which means they'd add up to 90. So the measure of angle 1, which is 2x plus 6, plus the measure of angle 2, which is 5x, would have to add up to 90 degrees. So 7x equals 84. Divide both sides by 7, and I get 12. But again, I'm looking for the measure of both angles, so I'm going to plug that 12 in, and I get that the measure of angle 1 is 2 times 12, 24, plus 6 is 30 degrees, which would make the measure of angle 2 60 degrees, since they add up to 90. So there's my two angles, and that is all the algebra examples that we have.